Thank you very much. So this is mostly a talk about climate change. And my interest in climate change started in 1982. I was 10 years old and I was at school, and our teacher told us about acid rain. And to 10-year-old me, acid rain was absolutely terrifying, because I had a vague idea about what acid was. I knew it was a clear liquid and I knew it melted things, and I worried that if I went out in acid rain, maybe it would melt me, and that doesn't sound very good. And it's a clear liquid, so how would you know? Wouldn't it be exactly the same as ordinary rain? Well, it turns out that acid rain doesn't melt people, so that's good, but it does do terrible things. It strips forests of their leaves, it leaches nutrients out of soils, it gets into rivers and lakes and pollutes those, and it does actually melt things. It melts sculptures and structures and those sorts of things. It's pretty bad. It's caused by a gas called sulfur dioxide, which is a gas that we emit when we burn coal. And because it's a gas, it doesn't pay any attention whatsoever to international borders. So emissions from the UK, where I'm from, would blow into Europe. Emissions from the USA would blow over to Canada, and they would fall as acid rain there. Those emissions were serious enough, they would cause major diplomatic incidents. So you might be wondering, why haven't you heard about acid rain in a while? And the reason is because we fixed it. So we signed international agreements. Those international agreements were extraordinarily effective. This is a graph that shows sulfur dioxide emissions, and if you look at it, you can hopefully see that the emissions from Europe fall by about 80%, from the US by about 90%, from the UK by about 98%. And the reason we don't talk about acid rain anymore is because we fixed it. We actually did something very similar with the ozone hole. So the ozone hole is caused by, again, a variety of gases. We signed the Montreal Agreement, and the effect of the Montreal Agreement was the emissions of those gases basically fell away to zero. It turns out that international agreements actually work. If you like having an ozone layer, and you should be a fan of international agreements. And I like to mention this because when you think about climate change, it's very easy to get caught in a kind of doom loop where you go, God, well, this is terrible, and we're all going to die, but with a bit of luck, I'll be dead and I won't notice or something. I'm not going to do anything because it sounds like it's just a problem we can't solve. And both acid rain and the ozone hole, I think, demonstrate that this is stuff that we can fix if we choose to fix. The next problem we have is the greenhouse gases. So again, this is a family of gases. It includes methane, carbon dioxide, nitrous oxide, those sorts of things. And they're really important. What they do is they trap heat. So heat from the sun passes through them, hits the earth, bounces off, and some of it is kept. They're really important because if we didn't have any greenhouse gases, the average temperature on the earth would be about minus 20 degrees centigrade, which is pretty chilly and too cold to sustain most life. The problem that we have is since 1850, the Industrial Revolution, we've been putting more and more greenhouse gases into the atmosphere, and because of that, we're slowly warming the planet up. That's what this graph, this is the hockey stick graph, the Bradley Manning graph, you've probably all seen it, but that's what this shows. So it goes from 1000 on the left-hand side. The blue shading area there is the margin of error, effectively. So obviously we don't have very good records in the 1000s, so the margin of error is wider, and then it narrows as our records get better. It's a graph of temperature anomaly, and probably, hopefully, what you can see is that it sort of bundles along, not doing very much, till 1850, and then it starts to climb. Now, the left-hand axis there goes from minus 0.8 to plus 0.6. So it's not big. It's not yet a big effect. Again, you probably know, I hope you do, that the scientific consensus on this is a warming above about 1.5 degrees is pretty bad. You probably also know that the most optimistic prediction for how much we will warm the planet this century is about 2.7, 2.8 degrees. That's the most optimistic estimate, and that's pretty damn cataclysmic, right? We have a problem, and we need to do something about it. But this is a tech conference, so why am I talking about that? Well, the reason is because as an industry, we do contribute. I did some research for the second edition of a book called The Cloud Native Attitude with Aaron Curry, and I was slightly surprised by some of these numbers. They were both better and worse than I thought they would be. So essentially what I discovered was that global data center emissions are between about 220 and about 320 terawatt hours. If you add data transmission networks in, which you kind of have to, there's not much point in a data center if you can't get stuff to and from it, you more or less double that number, okay? So what that means is as of 2001, the industry emissions from data centers is about the same as the emissions from a country like Brazil. It's significant. It has a bearing. Those numbers haven't risen all that much until very recently, which was the surprise to me. Because our data centers have got more efficient, even though we've been adding a lot more compute, the effect of adding more compute hasn't been to massively increase our emissions, at least our emissions from data centers, until very recently. The good news for low carbon technology is getting cheaper. So if you think about acid rain, the acid rain example, two things actually needed to be true for that to work. One was what I mentioned, the global legislation, but the other thing was the cost of installing sulfur scrubbers fell to a point where it was something that was a reasonable thing to do, right? It was expensive, but it wasn't budget breaking. And so what that meant was countries felt compelled to act because there was global legislation, but they also felt able to act because it wouldn't totally destroy their economies. The same thing is happening with low carbon technology. So the cost of solar panels has fallen by more than 90%, cost of wind energy by more than 70%, battery costs have also fallen, and a lot of this technology is getting a lot better. However, I don't think it's going to get better fast enough to be the answer on its own. There are climate scientists I have spoken to who think I'm a heretic at this point, but I'm just going to say I think nuclear energy is going to be part of this mixture for the foreseeable future. Nuclear energy is actually zero carbon. Has other problems, but it's zero carbon. If you want me to go into that in more detail, I can, but it'll have to be after the talk because unfortunately I don't have time now. But yeah, so that's good news. Low carbon technology is getting cheaper. As an industry, we have a significant bearing on the amount of carbon that we are emitting. Carbon is a greenhouse gas, it's heating the earth. So we need to do something about that. And at this point, we need some sort of strategy or roadmap or something so we can figure out where we're going. In my day job, I do a lot of consulting work with clients, and one of the tools I tend to use quite often is a maturity matrix. I love a maturity matrix because I can stick it in front of a client and go, you tell me where you are, and then we'll figure out how we get to where you want to be. It's a bit of a simplification, but it kind of works. In the case of green software, luckily for me, the Green Software Foundation has already made a maturity matrix for green software. This is what it looks like. There's a link there to the GitHub repo, so you can go and download this afterwards if you wish. And I'd encourage you to do so and to fill it in for your own organizations. If you do that, what you will probably discover is that you're somewhere over here on the left-hand side. Certainly most of the companies that I talk to are over here in what we call aspiring. Some of them aren't even quite at aspiring yet, I think. But anyway, generally they're going to be on the left-hand side of the graph. And that's okay, right? We have to start somewhere. And the good thing about being on the left-hand side of the graph is there are a bunch of things that you can do that are relatively straightforward that will make a massive difference to the amount of carbon you're responsible for, which is great. I'm going to do a very quick bit of terminology level setting just in case any of this isn't familiar. So over here, there's some stuff about scope 1, 2, and 3 carbon. Scope 1 and 2, 3 carbon is a definition that comes from something called the Greenhouse Gas Protocol. The Greenhouse Gas Protocol is the most widely recognized mechanism for reporting our carbon emissions. It's also slightly confusing, so let's just go through it very quickly. So your scope 1 emissions, those are the emissions that you're directly responsible for. So that's things like fuel combustion from your vehicles, those sorts of things. Your scope 2 emissions are the emissions that you're directly responsible for, but where you're purchasing stuff in. So that would include things like electricity and heating. The 2015 definition of the protocol actually goes into exactly what's in scope 2 in vast and tedious detail. So if you need more information on that, the 2015 definition is the one to look for. And then scope 3 is the rest of your supply chain. So that's essentially all the other stuff, including things like business travel that you are emitting as part of your operations. Scope 3 is going to be the biggest for pretty much any organization. It's also, by some way, the most difficult thing to report on. One of the things about the scopes is it may not be immediately obvious how that maps to what we all do as IT people. Again, luckily for me, the GSF has done the mapping for me. So this is their graph. Again, I've linked to the source of it there. And basically what you can see is private cloud, so your own data centers. The electricity is scope 2. The embodied carbon, that's to say the carbon that's used in the manufacture, transportation, and eventual destruction of your hardware, that's embodied carbon, that's scope 3. If you're running everything on public cloud, all of that is scope 3 because you're not buying anything directly. And fairly obviously, if you're doing hybrid, it's a bit of a mixture. So the energy that's running in your own data center is scope 2 and everything else is scope 3. Front end is also all scope 3 because it's running on other people's stuff. The other thing in here that I'm going to quickly cover off is carbon zero and carbon offsetting and all of that sort of thing, because again, I think these definitions can sometimes be a little confusing. To be carbon neutral, an organization has to track its scope 1 and 2 emissions, not notice its scope 3 emissions, just the 1 and 2, reduce them as much as it reasonably can, and then use carbon offsetting to get rid of the rest. Carbon offsetting, again, is quite controversial. Plenty of people will tell you it doesn't work. They're kind of right, sort of, but I think it has some value. Most organizations also include business travel in carbon neutral, although they're not actually required to do so. Net zero basically means you reduce your emissions as far as you possibly can, and then you use carbon removal to take care of the rest of it. Some of the technology we need for carbon removal doesn't actually exist yet, so that's a little bit alarming. But for us as IT professionals, that's less of a problem, which is good news. Over on the far right-hand side of the graph, we have this inspiring column. So what does it mean to be inspiring? Well, one of the things it means is to be net zero in terms of the carbon we're using in our data, or the electricity, sorry, we're using in our data centers. So basically, all of the energy that you're using in your data center is time matched to green energy on the grid. Okay, making sense? The other thing in here is 10-year life expectancy on all of your end user hardware. Quick show of hands, who's got a 10-year-old mobile phone they're currently using? Nobody, right? None of us have. 10-year-old laptops? No, probably not. You do. Wow, that's ace. Congratulations, you are ahead of everybody else in the room. That's fantastic. The reason for the 10-year thing on end-user devices is because with an end-user device, the embodied carbon absolutely dwarfs the carbon that's used in its lifetime. I've linked there to the iPhone 14 environmental report from Apple. I chose the iPhone 14 because it's the easiest report to read. And from memory, the embodied carbon, so the carbon emitted in manufacture of an iPhone is about 78% of all of the carbon that it will ever emit. About another 12% is transportation, getting it to somewhere where you can sell it. About 2% is used in destruction at the end of its lifetime, and the rest is the carbon that's emitted during charging. Because of that, what you want to be doing is making less devices, which is a bit anti-capitalist, which is a shame. But that is kind of what you want to do. So you want to be extending the life. So if you're thinking about buying end-user devices, whether that's individually or making corporate type purchasing decisions, think about the devices that get supported the longest and last the longest, and try and buy those, and try and get out of this business of upgrading every couple of years because there's a new shiny processor. Okay. That's the level setting bit. So now we're going to get into the details. So we want to make ourselves more efficient, and obviously we're all programmers. So what we're going to do is we're going to run a bunch of benchmarks to figure out what the most efficient programming languages are. Here's one. That'll tell you that C and C++ and Rust, in roughly that order, are the most efficient programming languages. And so that's what we're going to do. We're going to rewrite everything in C or C++ or Rust. No, we're not. There are a couple of reasons why we're not going to do that. There's a business reason, but there's also a tech reason. The business reason is to do with time to value. So if I look back over the whole of my IT career, which is 30 years or something at this point, I would argue that every single thing that happened that mattered in our industry was about reducing time to value. It was about being able to get from having a brilliant idea in the morning to being able to get that in front of a customer as quickly as possible. Right, that kind of explains things like Visual Basic and Java and C#. It explains public cloud, it explains Agile, it explains fast flow and team topologies and all of these other things. They are all at some level about being able to get stuff to our customers faster so we can validate them. There are other reasons, but that's one of the reasons. What that means, though, is if you go to your boss and say, we want to be more carbon efficient and therefore we're going to rewrite everything in C and C++ and Rust, she is going to turn around to you and go, no, we're not. That's a stupid idea because we would be bust. And she's right. It is a stupid idea. Rewrites are horrible anyway. You don't want to do them. Trust me, I've done one. Don't. So that's not what we're going to do. Also, it's a little hard to see, but there's Java on this particular benchmark. It's better than you probably thought it was, unless you've looked before. The JVM is actually a brilliant piece of technology, and it's a brilliant piece of technology because lots of really smart people have spent a lot of time making it better, optimizing it in a variety of different ways. What that means is you're much better off using the latest versions of the runtimes and the frameworks that you can so that you get those benefits, okay? So, use the latest long-term support version of Java if you can. Think about the frameworks you're using. So Holly was here yesterday speaking about Quarkus and efficiency. The Quarkus team at Red Hat have done amazing work to make Quarkus more efficient in a variety of ways. So that is going to have an impact. So yeah, use the latest versions. Even Python, which is languishing down the bottom of that table, is getting better. There are limits to what you can do with Python because Python. But there is a certain amount you can do, and a lot of good work is going on, but you're only going to get that benefit if you're using the most recent version of the runtime. So that's the business reason, but there's also a technology reason. And the technology reason is something called energy proportionality. It's a terrible name. Naming things is hard. What it actually means is energy disproportionality, which is confusing. So this is an observation. It came out of Google. Again, I've linked the paper there if you want it. That when you turn a server on, the static power draw is about 50% for an energy efficient server. It's much worse for a less energy efficient server. So you turn a server on, static power draw is 50%, which basically means if you're using fossil fuel powered electricity, you're emitting half of the carbon doing literally nothing useful, which is interesting. And it turns out that the optimum point is over 50%. So that if you look at the graph there on the right-hand side, basically 50 to about 80% is the sort of optimal envelope for the efficiency of your server. That's the point where the level of useful work to carbon emissions is best. Beyond about 80%, you start getting, CPU contention, queuing contention, those sorts of things. So that's not great. Between 50 and 80% is about what you want. And as I said, that's actually worse if your server is less efficient. So a good first goal, if you're running things in your own data center, is to go for machine utilization at greater than or equal to 50%. I said that to a prospect, not a client, a prospect last week, and they looked at me and went, sounds bloody difficult. And they're right, it is. It's a bit easier for public clouds because public clouds can do stuff with spot instance, multi-tenancy and those sorts of things to get the utilization up. But one of the reasons this is hard is a bit of sort of folk memory that I think we still have as an industry, which is that we tend to over-provision as a risk management strategy. Those of you that are sort of my age or a bit older might remember that procurement used to be unbelievably slow. In some organizations, it still is. But what that meant was if you wanted a server, someone had to buy the server, put the software on it, rack it, get it into a cluster, and that whole process was usually measured in like weeks or perhaps months. And what that meant was if someone was asking you to estimate how much hardware you needed, you tended to overestimate. So you'd say, I don't know, I've got 500 retail stores, I've got 4 PCs in each retail store. That means I could have 2,000 people using my application at any one time. So that never happens, but let's pretend it does. I'll write a load test using something like Mercury, or God help us, and simulate that load, and then that will tell me how many servers I need. So say that comes out as 4 servers, and then what I'll do is I'll go to procurement and say, 8 servers, please. And no one ever says, why do you need 8 servers? And no one ever goes and looks afterwards at what those servers are doing. Like literally that never happens. And that problem is actually slightly worse than you think because of the effect of zombie servers. So zombie servers are servers that were once doing something useful, but no longer are, right? They have an app on them that nobody uses, but it's still sitting there and we haven't realized, so we haven't requisitioned them. That's what a zombie server looks like. Obviously not really. And zombies are bad, right? We want to get rid of them. How bad? Well, there's a story in Building Green Software, which is the Anne Curry, Sarah Bergman, Sarah Sue book, from VMware. This is from Martin Lippert, who's Spring Tools lead and also a sustainability advocate at VMware Broadcom. And he says that in 2019, VMware consolidated a data center in Singapore. The team wanted to move the entire data center and therefore investigated what needed a migration. The result was somewhat shocking. 66% of all host machines, 66% were zombies. More than half. This is pretty astonishing. That's obviously terrible for the environment. It's terrible for your bottom line because you're paying money for that stuff that you don't need. It's also not brilliant for your security posture because what tends to happen with zombie servers is they don't get maintained properly. And so you're opening up your attack vector. There's actually another quote. This is from Ed Harrison, who is head of security at Metaswitch Networks. And he says that some of the biggest cybersecurity incidents in recent times have stemmed from systems which no one knew about and should never have been turned on. The trouble with zombie servers is, how do you recognize them? Sadly, they don't look like the pretty picture I showed you. They look like any other server. There is a thing you can do. It's called a scream test. What you do is you turn the server off and you wait to see if anybody screams. It doesn't usually make you all that popular, though. You can automate it. People have. So you can write like a bit of scripting or something that basically monitors your servers and goes, this server doesn't appear to do anything. I'll turn it off and see if anyone notices. That tends to make you very unpopular. And the reason it makes you very unpopular is because we have this worry that when we turn our servers off and turn them back on again, they don't come back in the same state. And you've probably all experienced that. I think I certainly have. The best encapsulation of this I've heard is from Holly Cunnings again. She calls it LightSwitchOps. It's actually made it onto the maturity matrix, although they slightly misspelt it, which annoys me every single time I see it. But nevertheless, it is there, so that's good. This is this idea that basically you should be able to shut a server down and bring it back up again reliably. A good place to start with that is your Q&A and test environments, if you have those still. Get into the habit of shutting those down at evenings and weekends and whatever times you're not using them, because that will get you into the habit of getting your servers to a point where they come back reliably, and then you can think about expanding it into production. If your business isn't global, fairly obviously, you can also think about scaling your servers up and down according to your predicted peak demand. That's quite a good thing to do. Lots of us don't, but you can. Again, that's worthwhile. So run an audit, find out what your servers are doing, get rid of the ones you don't need. And if you know you can bring them up reliably, you can afford to be more brutal because you're not likely to get fired because something goes down for a bit, probably. The other thing you can think about is auto-scaling, fairly obviously. So Kubernetes has auto-scaling built in now. Most of the big cloud providers have auto-scaling. Something I have found is that people tend to be a lot happier about scaling up than scaling back down again, which is a pity because you're kind of missing the point. But you do, if you're enabling auto-scaling, you want to make sure that it's both directions. If you're still running stuff in your own data centers, you do actually have some wins. Most of the wins in this stuff are in public cloud, to be honest, but there are some things you can do in your data centers. One of those things is you have control over a lifetime of your hardware. There's a reason, though, why we don't talk about 10-year life expectancy on servers, well as we do on end-user devices, and that's because the calculation is much more complicated. Servers get more efficient, generally, somewhat, and so the trade-offs are not quite the same. But you do have a choice, right? You can run some numbers, you can do the maths and have a look at it. So it's worth thinking about, should I be replacing this server or should I be extending its lifetime? You can also take advantage of the power saving features that are already built into your servers. Just enable that stuff so the server goes to an idle state when it's not doing anything. You do need to test that. I have had servers that go to an idle state and then don't wake up on incoming network traffic and nobody seems to know why, and it's very annoying. So you do need to test it. Again, as an industry, we have a bit of an aversion to power saving, though I don't really know why. It's worth doing. CPU choice also makes a difference depending on your workload and your scale. So if you're running a lot of stuff at scale, CPUs are more or less efficient. You need to benchmark this yourself because it will vary for your workloads. I will say that my experience is essentially Intel is generally the worst in terms of efficiency for pretty much everything that I look at anyway. AMD is a bit better, ARM is a bit better still. Obviously Intel and AMD are more interchangeable. Again, if you're running on public clouds, that's literally just ticking the AMD instance on the VMware or whatever, the VM instance you're using. So that's good. But you also have that choice in your own data centers. The other thing you can do in your own data center is look at voltage range. So your server has a range of voltages that it supports. Look at what the lowest one is, and can you supply that to a server? Again, that will make a difference. It's a perfectly reasonable thing. I mean, it's a little esoteric maybe, but it's a perfectly reasonable thing to do. And again, if you're operating at scale, that will make a bit of a difference. So there are some advantages you have in your own data center, though I have to say not that many. The next thing I want to talk about is measurement. There's a sort of maxim in our industry that you can't fix a thing you can't measure, and that's bad news for those of us that care about carbon, because measuring carbon is actually quite hard still. A lot of the time what we end up doing is relying on proxies. CPU utilization, as we looked at earlier, is actually quite a good proxy. Cost is also a good proxy, though only up to a point. The reason cost is a good proxy is basically because a lot of your cost is your energy use. So if you bring your energy use down, that makes a difference. The reason it's imperfect is because the carbon cost is not normally factored into the cost of the electricity you buy. The thing about carbon is that's a cost that's not borne by you as an individual or you as a company. It's borne by the society, which is unfortunate, but that's how it works. There is an interesting thing, though, which is because we are terribly profligate as an industry, we can make a huge difference just by bringing our costs down. So in Bill Gates' book, How to Avoid a Climate Disaster, he talks about something called green premium. So he calculates the cost of going green for different industries. I would argue that in our industry, I suspect our green premium is a negative number, probably. I think it will actually be cheaper for us to be environmentally sound than what we do at the moment, probably. Can't be absolutely certain, but I think so. So that's why cost works as a proxy. You can do, if you're running on public cloud, then the public cloud providers all have strong sustainability goals, and they also have tooling that you can use to look at your carbon emissions. So again, I've got those on the slide there. AWS has customer carbon footprint tool, Azure has the emissions impact dashboard, and Google Cloud has carbon footprint. I'm sorry about the sound problems. So those are, again, those are tools you can use. They're pretty sound. There are papers behind them that you can go and read. I have read the Google one particularly, and it's pretty solid in terms of the methodology. It's pretty good. There is an open source option as well. That's Cloud Carbon Footprint, sponsored by ThoughtWorks, and works obviously across different public clouds. So that is another option. You might be able to adapt that to use in your own data center, but I'm not sure. So yeah, the GSF has a formula. I don't have time to go into the formula in detail. It's quite neat, actually, quite elegant, a very simple formula. I've linked to a blog post which describes it in more detail. What I will say is that the formula has a location element. For a fairly obvious reason, actually, which is that the energy mix in different locations is different. So if you're running on EC1, that's in Virginia. Virginia is a coal-fired state. That means your carbon footprint is enormous. Don't run anything in EC1. Yeah, location matters. There's a tool called electricity maps, which allows you to have a look at the carbon mix of the energy that you're using. If you've got the luxury of picking where your workloads are running, then electricity mapper is a really helpful tool. It's real-time information. It's pretty accurate. They partner with people like Google and AWS and Salesforce. It's really pretty good. So a really simple quick win is just stick your workloads in somewhere where the energy is greenest most of the time. In that sense, it's like super easy. There is a slightly more advanced thing you can do, and that slightly more advanced thing is demand shifting. So there are APIs, not time as well, WATT. The carbon aware SDK from the GSF is another. With an API, what you can do is you can make predictions about the greenness of the workload and scale up and scale down your compute accordingly. Which is I think is just a really interesting and powerful technique. That can be time-based, so you can think about batching stuff and caching, and like doing doing cache discards and requerying when the energy is green. But you can also do location-based. So you could have workloads that follow the sun or follow the wind around. Obviously a bit more difficult, depends on the workloads, but it is stuff that you can do that people are doing. Some of the things that we've learned to do because microservices became fashionable, and so we all had to learn how to do distributed computing, turn out to be things that you can apply in a carbon-aware way. So an example of that would be something like graceful degradation. So Netflix historically used to do this a lot, and services got a lot more resilient, so it happens less. But if you go to the Netflix homepage and can't get the movie recommendations because the movie recommendation service isn't available, it just retrieves some stale movie recommendations from the cache. You, as technical people, probably notice that sort of thing happen, but most people don't. And in fact, Netflix used to do this all the time. As I say, they've got a bit more resilience. It happens less often than they used to. But there's no reason why you couldn't do exactly the same sorts of things, but in a carbon-aware way. So, do a cache discard at the point when the energy is greenest, do the refresh then, and then serve from the cache the rest of the time. There are a whole bunch of these sorts of techniques that we could apply, and we're starting to see that happening in the real world. So Google has launched a project to make its
cloud workloads more carbon aware. It says it can shift, move, or compute tasks between different data centers based on regionally hourly carbon-free energy. Link to the paper there if it's reading about that. Microsoft has done something with Windows 11, where Windows 11 will basically do Windows updates based on predictions of when the energy is going to be greenest wherever the device is running, which is pretty cool. They've done something similar with Xbox. So again, Xbox will do its updates when the energy is predicted to be greenest. They also introduced shutdown, which is basically low power mode again. And they say that can reduce carbon emissions from the Xbox by about 20 times, which is pretty profound. There are a lot of easy wins here. There are a lot of things we can do that are actually quite straightforward. I'll also mention that Apple has clean energy charging for iPhone. I think this is still US only, as far as I know. I'm not on the most recent version of iOS, so I'm not absolutely sure, but I think it is. But again, it's basically doing the same thing. It's looking at predictions for when the energy is greenest and charging the iPhone at that point. Obviously, we saw earlier that the embodied carbon is actually a bigger problem for things like iPhones and Xboxes, so actually extending the life of the product is more important, but I'm still glad to see this. Right, it's 2024, and this is a conference talk, so obviously I have to have an AI bit. That's the rules. Doing the AI bit of this talk turns out to be incredibly difficult. And the reason it's incredibly difficult is because the people who are making AI stuff really don't want you to think about this, and so they won't tell you much. I'm going to pick on OpenAI for a minute. The ChatGPT-3 paper is actually quite informative. It tells you how much carbon was burned to train ChatGPT-3. The ChatGPT-4 paper, on the other hand, contains almost no useful information of any kind that I can discern. It's pretty useless. So we have to look at other sources. The good news is that most big tech companies do quite solid environmental reporting. So we can look at the environmental reports. Microsoft reported in May that carbon emissions have risen by about 30% since 2020. And that's primarily due to the construction of data centers to move to support its push into generative AI. Not great. Google's emissions have surged about 50% since 2019 and about 13% year on year last year, 2023, again, according to their own reporting. By the way, those numbers are probably underestimates if they are anything. Generative AI is expensive. It's computationally expensive. Training is expensive. There is work going on to make this better. You can do stuff with sparseness and all sorts of things that helps, but it's still expensive. And what slightly frustrates me about this is it's a choice, right? There's nothing latency sensitive about training a machine learning model, which means that you could decide to train your machine learning model 100% on renewable energy. It would just take a bit longer. The problem is that as an industry, that's not a trade-off we're prepared to make, because people tell us we're late or we're behind or whatever. So we feel that this tremendous pressure to be ahead all the time. And because we don't bear the cost of the carbon, it's that cost is borne by society, we don't really care about it, which is a shame. How much difference would it make if we did care about it? So there's some research that came out of University College Dublin. They found that practicing time-shifting methodologies, the methodology we were just looking at, would reduce software-related carbon emissions for machine learning workloads by between 45 and 99%. It's pretty huge. It's pretty significant. I find it very frustrating that we don't. If you're using a generative AI model, if you're being asked to use a generative AI model, fairly obviously think about whether a pre-trained model will do what you need. Maybe you can use RAG or something to make it irrelevant to your use case. Don't train from scratch unless you absolutely have to. If you do need to train from scratch, do you need a large language model or would a small language model, maybe smaller corpus of text, would that work for your particular use case? Again, think about that. But also keep in mind that the training cost is actually not where a lot of the cost is. Because it turns out that running large language models in production is really quite expensive as well. And actually that's worse than training. In fact, we'll see a lot of AI companies are putting out papers on that go, oh, training isn't as bad as you think it is. It's terrible, but it's not as bad as you think it is. It's sort of a greenwashing thing. Because actually a lot of the cost is running adapting afterwards. But what that means is that a lot of the techniques we've already talked about apply just as well to machine learning as they do to everything else. So make sound choices. Not all large language models are the same. Meta is not my favorite company, but Meta's Opt175B, which is their GPT-3 equivalent, was trained using about 1/7 of the carbon of GPT-3. We can't do the GPT-4 comparison because OpenAI won't use the numbers. I will say as well that Apple, because Apple is pushing generative AI in their own very numbered way, they have said that they get enough benefit from their own silicon, which I'm assuming is ARM-based. I don't know what the use for the generative AI cloud. I don't know what that is. I'm assuming it's ARM-based. But basically, they've said it's sufficient enough that they're able to do this and still be net zero by 2030 for carbon emissions, for data center emissions at least. So that's encouraging. So you do have choices here. There are things that you can do that will help and make a difference. In terms of what's coming, so again, going back to acid rain, there were two things that needed to be true. Costs needed to come down, but global legislation also needed to happen. I think the same is basically going to be true of greenhouse gases. ESG already exists. Lots of companies look at ESG scores. ESG is fairly imperfect. It's quite easy to gain the environmental bit of ESG in various ways. Lots of people do, unfortunately, but it's a start. The EU has CBAM, which is essentially a carbon tax. I believe it's the first carbon tax anywhere in the world. I suspect it'll end up being a little bit like GDPR in that everyone will go, God, that's terrible, and everyone will copy it or something like it. I think it'll be quite similar. I personally think we need legislation to take some of the carbon cost back to the organisations that's responsible for it. Personally. Again, not everyone else would agree with me. Okay, so those are some of the things we could do. What else can we do? Well, if we want to get a sustainability initiative off our company, the people that we need to be talking to are our CFO, because it's going to be saving us money, our head of security, because it improves our security posture, and also maybe our head of recruitment. It doesn't always feel like it, but there is still kind of a war for talent in our industry that we need more programmers than we have. More people care about this than they used to. When I first talked about this, literally nobody cared, nobody in the room at all. So I'm delighted there are a few people here, even though Dan North is speaking somewhere else. So thank you for that. So I think your head of recruitment might be another ally if we're trying to get one of these initiatives off the ground. You can also put pressure on your vendor. Adrian Cockcroft, who's head of sustainability at AWS and fully retired, was very open about the fact that AWS had strong sustainability goals because their customers kept telling them they couldn't. That was the only reason Jeff Bezos is not a climate warrior. He did it because his customers kept telling him that he should. You can put pressure on your vendors, and if enough of us put pressure on our vendors will start to take this stuff seriously. With some caution, I would also recommend that if you are using a large open source library a lot, you could talk to the maintainers of that open source library about sustainability as well. The reason I emphasize the caution here is because you all probably know, being an open source maintainer is not a joyful thing much of the time. You know a lot of things to worry about, and sustainability may not be the highest one. But again, look for options that have a strong sustainability story, and have those options where you can, and think about what you can do to help. Finally, this is a very new and nascent field. There is not a lot of information that I've made. It's changing really quickly, which means a lot of what I've just told you will probably not be true in a year or two, unfortunately. So if you or your organization are doing any good work in this space, please share that information with other people. There's an absolute dearth of this. So speak at conferences, write case studies, publish blogs, do videos, whatever medium you want to use, please share your knowledge on this. As an industry, knowledge sharing is the most important, knowledge workers. So knowledge sharing is the most important thing any of us can do to drive something forward that you care about. So if you care about this, please share your knowledge. If you've no idea how to do that, I was chief editor at InfoQ for 6 years. I've trained hundreds of developers how to do this kind of thing. Reach out to me. I'm very, very happy to help in any way I can. If you want to learn more about the subject, these are the books I would recommend. Also, Building Green Software, new from O'Reilly. I think it's on the bookstore still. It was this morning when I went to check. It's a fantastic book. It's quite an easy read. It's actually quite funny because it's hilarious. And it's full of really solid advice. There's the Cloud-Native Attitude book. So that's also kind of anchored with a tiny bit of help from me on the second edition. That has a chapter on sustainability. It also has a bunch of case studies that are long-term. So they went back to companies over multiple years. And some of those have sustainability stories. It's quite a nice introduction. It's also free. You can download it from the Container Solutions website. Bill Gates' book, How to Avoid a Climate Disaster, again, I really like. It's quite an easy read. It's pretty solid. He writes very well. And Hannah Ritchie's book, Not the End of the World, is one of the most optimistic books about climate change I've personally read. And it very much chimes with my own thinking. So, confirmation of that as a friend. But I think it's a really great book, and I'd strongly recommend you read it. If you like a podcast, the Climate Stack podcast is new. I think there are 4 episodes so far. We'll see if I keep it going. I was a guest on one of those episodes, but don't hold that against it. It's actually a really good podcast. And building ring software. So Anne Curry does public training courses and private training courses, so she can go out into organizations to do training. I did the first iteration of the building ring software training course with her, and it was great. She's a wonderful communicator and a fantastic person anyway. So again, strongly recommend that if you want to learn more. Obviously, training may be beyond your budget, but if it's not, that's a really, really good option. And with that, even though we had sound problems, I'm done. Thank you very much for listening.